All right, let's welcome everyone back to part two for our quiz, our test, that is, not our quiz, on potential energy, kinetic energy, thermal energy, the properties of matter in the universe. So we talked in part one, we talked about potential energy, kinetic energy, and thermal energy. We left off on temperature. So let's look at temperature. Well, first, we'll look at Mercury. Mercury is, well, used to be in thermometers. It's not anymore because of its toxicity. It's banned in school. It hasn't been used in years in schools, but it's used in labs. But they're also moving now to digital thermometers, which are much more accurate than mercury. But mercury is much better than an alcohol based, which we use in school. Mercury has a much lower freezing point than water and alcohol based solutions, and a higher boiling point. But mercury has a toxicity to it. And so if you look at here, this is just an example of what we're using for alcohol-based solutions. Mercury has a higher boiling point and so forth, and it expands at a better rate than the alcohol-based solutions. So that's why alcohol is not as good as mercury. It does a good job though in schools. And there it is. There's quicksilver. That is mercury. That is what mercury looks like. It does not look red. There is a couple of myths on mercury, and we'll talk about those myths on mercury in a minute. But mercury, the problem with mercury is also it's found in a lot of fish. And so the ones you should try to avoid, not completely avoid, but don't eat them so much. Here's where it's high, right? In swordfish, in shark, also called mako in stores. They'll sell mako. Try to avoid this at times. Once a month is okay. A medium risk is tuna. Tuna fish. You can have tuna maybe 2 times a week. 2 times a week's fine. And then there's really low risk in salmon and flounder and some trout and so forth. So either the river fishes or the fishes that you see closer to the shore, but those out deeper into the ocean, you want to be wary on the mercury level on that. Now the myths on mercury. Close this out. There's two myths. One is that people used to think that the mercury was dyed in the thermometers. No, it was not mercury. If you ever see a thermometer and it has red, it is, well, especially nowadays, it is definitely dyed alcohol. It's an alcohol-based solution. Mercury is silver. So if you see a thermometer that has silver in it, it's probably mercury, but you probably won't find them too often. The other myth is that people used to think there was this, and there's some people that probably still do, but they used to think there was this magical element called red mercury. Red mercury. And that's probably where the myth comes that we think mercury is red. Red mercury, they thought, was magical. And people have done this. All societies have done this so many times in the past, like Ponce de Leon was searching for the Fountain of Youth in Florida. They were looking for the lost city of gold, El Dorado, in the United States. Before it was the United States, everyone's looking for some kind of magical thing. And they thought that this red mercury was inside these pyramids. It was stuck in the bones of the pharaohs. So people were looking for that, and they thought it was magical. But no, red mercury does not exist. It's just a myth. So going back to temperature, we should know that the more massive an object is, the longer it takes to heat up, and the longer it takes to cool down. Remember, temperature is the average kinetic energy of a particle. So again, if it's more massive, like here, this one is bigger than B, so it has more water, it has more space, it takes longer for this kinetic energy to heat up and move around. It also takes longer to cool down. So the bigger it is, the longer it takes to heat up or cool down. Something to remember. And just to review thermal energy is the sum of kinetic and potential energy, whereas temperature is the average kinetic energy. So try to remember this point right here. And again, heat is just the flow of thermal energy. And if you were unsure about thermal energy, go to the part 1 of this video. So let's look at this now. We know that metals conduct electricity and heat the best. The best was silver. Not was, but is. Followed by copper. If you had copper pots, and they still sell copper pots, silver pots are just too expensive. But copper pots would heat up your food faster. If you were boiling pasta, the water would boil faster if you had copper. But we have the thermal energy, and here's the heat coming off, the radiation. So not all radiation is bad. We'll talk about radiation in a minute. But this radiation is causing heat, right? So the heat and when we're talking about conduction, it's always solid to solid. Solid to solid. So the heat would go from this stainless steel pot or a copper pot, and it will go up the handle. Now, if this was a completely steel handle or a metal handle, it will get to your hand very quickly, and you would burn your hand. That's why these handles here have some kind of insulator, like a rubber or something, so it would block that heat. That's conduction, solid to solid. Whereas convection is, we're talking liquids with convection. And you can see it here. The water is heating up on the bottom, and then hot air rises, hot water will rise, and it'll push the cold air, the cold particles down. They'll get hot, and they'll move up until we form an equilibrium. Everything's hot. And as the water gets hotter and hotter, it will boil, and then you will get gas molecules rising, right? So again, there's types of radiations we're going to talk about. There's alpha, beta, gamma, there's microwave, there's X-ray, bunch of them, right? And let's look at the type here from the chart. As you can see, we'll get that page marker out. What should we use now? We use blue. Let's use blue. So alpha radiation could be blocked by just by your hand or by paper. If you had a paper house, alpha's not getting in. With beta, you need aluminum. So if you had your soda can, you can block beta because your soda can's made of aluminum or aluminium, whatever you want to say. Chemical suit can block you. Charcoal and aluminum could block you from beta radiation. Gamma, though, it'll go through paper and aluminum, but it will be blocked by thick lead. And they use lead at the dentist's office. They use lead to block when they take X-rays, because X-rays and gamma rays are dangerous. Water is also good to block gamma rays, but not as good as thick lead. But then there's neutron rays, and they're very rare, so you don't have to worry about neutron rays. But if there was a neutron ray leak somewhere, which again is very rare, it would go through the aluminum. It'll even go through lead, but it will be blocked by concrete and water. All right, and there's other types of radiation. So these are the dangerous types. In the electromagnetic spectrum, you see the green, so we'll use green. Let me just get that green marker. Where's green? Where are you, green? There we go. Green. So the green, the X-rays, and the gamma rays are very deadly. The ultraviolet rays can be deadly. We'll talk about them in a minute. Microwaves could be deadly too. Aluminum, though, if your microwave has aluminum around it, not inside of it, because that'll cause fire, but there's aluminum that could block and the glass can block the microwaves from getting to you. But over here, of course, this is the more deadly, the deadlier, I should say. So let's look at the ultraviolet rays. We talked about this in class. And there's infrared. And if you had infrared, you can see in the dark. You can see the heat from this topo, this little mouse. And here are the animals that have it. Snakes, frogs, mosquitoes. Mosquitoes can see the heat from our bodies, and we're targets outside because they want our blood. All right, here's UV light. So there's 3 types, A, B, and C. C doesn't get into our atmosphere. Just remember that. There's no C that we can see. Well, we can't see A or B, but there's no C that comes into Earth, so we don't have to worry about C. Just remember that. C does not enter Earth's atmosphere. But we have A for aging. That's how you can remember it. A for aging, B for burns. So let's get our page marker back up. Where are you? All right, there we are. All right, so A for aging. The UVAs over time, if you spend a lot of time in the sun and you don't protect your skin, you don't put on that special protection, the AV rays can wrinkle your skin. Be careful. You can go out in the sun, but you want to protect yourself. You don't want to stay out too long, especially at the beach. You want to be careful. The UVA rays are out all the time. UVB rays, they don't come out all the time. In New York, though, they're only out to about 11 to 3. And again, this is not exact. It could be 10:15. Well, not that. It could be like 10:30 to 2:30, 3:30. Mostly this is an average when they're out. And the UVB rays are responsible to give us vitamin D. That's what we want. We want the vitamin D. You don't have to spend too long to get vitamin D, to get when you're in the sun, when you want to get vitamin D. 20 minutes. 20 minutes. Even less. 20 minutes out in the sun gives you enough vitamin D. Now, vitamin D, again, even though it's 11 to 3, you still don't get these UVB rays in New York. You can get them in other parts of the country, but in New York, mostly up north in the northern latitudes, usually anywhere between April and probably the end of October or the beginning. That's really when you're getting the vitamin D. And you get enough. If you did this, if you followed this 20 minutes a day or less, just getting some UVB rays at this time, you can get enough vitamin D for the year. So you don't need to know all this other stuff here, but you should know that we have a Venn diagram here, and this is this is what they both share. They both can damage the skin. They both can penetrate through clouds. So don't think because it's a cloudy day you're not getting them. And so you can protect yourself from both of them. Right? You can protect yourself by that. Now, when you want to get UVB rays, again, you need to have some of your skin showing, right? You need to at least show your arms and your legs if you really want to get the vitamin D. If you're just wearing long sleeves and pants, you're not getting enough of that vitamin D from the UV rays. All right, leave that up for 1 second till you can see it. And again, just because you're feeling the sun, like in your car or inside your house, doesn't mean you're getting the vitamin D, because UVB rays cannot penetrate through glass. You can get the heat. You feel the heat. You definitely feel the heat, but those rays itself don't penetrate through glass. All right, let's look at properties of matter now. Let's look at the universe. The universe is extremely large. It's 14 billion years old. It's longer than 14 billion years old. And it has millions upon billions of galaxies. You see right here, these are not stars you're seeing. These are galaxies, and there's billions of them. And we have one, we're in the Milky Way. That's only one galaxy over a billion, right? So, here we are, that little dot. That's us. And we can only see a certain part of our universe, right? We can only see a certain part of it. The universe is vast and it's expanding. We'll talk about how it's expanding more when we talk about dark energy. So here it is. There's dark energy. So dark energy is mysterious. We don't know much about dark energy. We do know that it is expanding the universe at an extremely high rate. And it makes up most of the universe. Most of the universe is made of dark energy, which we talked about, 68%. And again, it's pushing everything away from each other. Whereas dark matter makes about 27%, and you don't need to know these exact numbers. And dark matter keeps the stars together, keeps stars in the galaxy together. So it really just keeps the galaxy together. So if it wasn't for dark matter, the Milky Way would just fall apart. So we need dark matter. We know we need dark matter, even though we can't touch it, see it, feel it. But we know it's there because something is keeping the galaxy together. And we're going to talk more about this when we talk about space in a couple of months. So the rest of the universe, the one that we can see, and that's only 5%. So everything that we know of, everything from your dog, your cat, the aloe vera plant, right? Aunt Sally, your car, the Twinkie, anything that you can see, feel, taste is made of matter. And then, of course, is the antimatter, which there's none left in the universe, or maybe a few traces, or just a few traces, or not even. We are making them in the lab. We're going to talk about that in the laboratory in CERN, which is in Switzerland. They have made antimatter. They're trying to make more. So right now they've made about 15 nanograms, a very, very small amount. They've made 15 nanograms, and that costs trillions of dollars just to make. It's an enormous amount of energy to make antimatter. And the danger, of course, with antimatter is if antimatter and matter got together, they would explode. So if you met your antimatter self, which there isn't any, but if you did and shook hands, you would explode. You both would explode. So if we're going to create this antimatter and it got in contact with matter, there would be an explosion, right? They would, what it is first of all, this antimatter, we only created 15 nanograms of it. We have to find a way to trap it. And they found ways, and it's called a penning trap. So these penning traps at CERN, we'll talk more about this later, these penning traps right here, they hold antimatter. And again, we only made 15 nanograms. Very, very small amount. If we ever made a gram, and we don't really have the technology or the money right now to do that, but if we ever did that, that'll be the equivalent of a nuclear bomb. And a gram is very small as it is. So you can imagine the energy potential in antimatter. Just remember, though, antimatter and matter, if they get together, that's an explosion. They will destroy each other. And here's our Milky Way. This is where we live, one of billions of galaxies. And we live, let's put up the page marker. Let's use a different color. Why don't we use blue? There we go. So we live about here. That's where we live. We live in something called the Orion Arm. And actually, that's really not that. Let's do that again. Let's use a different color. There we go. So, again, we live there, right here. That's better. The Orion Arm is where we live, the Orion Arm. Over here in the center, though, there is a black hole in our Milky Way galaxy. And our Milky Way galaxy is about 100,000 light years across. Enormous amount. It takes light from here to here. It would take light 100,000 years to get there. And remember the speed of light. It's 186,000 miles per second. All right. All right, so let's move on here. And so again, there's the Orion Arm where we live. And remember, all the galaxies we have in our solar system, that's the only stars we see. Not all the stars in our solar system. Let's rewind the tape. All the stars in our Milky Way are the only ones we see in the night sky. We do not see any of the other galaxies' stars. We can see the other galaxies. We can see they just in the night sky with telescopes. They just look like a little blob of white streaks, right? So here is our closest ones, and we talked about Andromeda a lot in class. There's also dwarf galaxies, very small ones close to the Milky Way, but these are our major ones. So Andromeda is our closest. Andromeda is about 2.5 million light years away. Again, so when we look at Andromeda in the night sky, it just looks like a little blob of white. It took 2.5 million light years for us to look at that. The light that left Andromeda reached us in 2.5 million years. Just an enormous amount of space. And Andromeda and the Milky Way are coming together. Maybe in 10 billion years they'll come together and collide. But as you can see, we have other galaxies close by. Here's another one. There's one. There's one. Now, when we mean close by in terms of the Milky Way, for us, they're extremely far apart. But again, remember, these are only a few galaxies, and there are billions of them. Just like there's billions of stars. Billions of everything. And here's Betelgeuse. We talked about Betelgeuse. Betelgeuse is in our Milky Way. Again, we only see the stars in the Milky Way. We don't see the stars in Andromeda. And Betelgeuse, this is Orion's belt. And you can see this in the winter at night. If you go outside in the southern sky at night, you can see Orion's belt. And if you look over here, you'll see Betelgeuse. It has a kind of a yellowish glow to it. And Betelgeuse is enormous. It's a very big star. If it was in our solar system, it would go all the way out past the orbit of Mars. It's much bigger than our sun. But it's also much younger. It's only about 100 million years old. It's 100 million years old. Our star, the sun, is 5 billion years old. But Betelgeuse, even though it's young, it's only 100 million years old, it is dying because it's so big. It is a red giant, and of course you're not seeing that in the sky. And it will eventually blow up. In fact, it could have blown up already. Betelgeuse is about 700, no, about 600, 642 to be exact, light years away. So when you're looking at Betelgeuse in the night sky, you're looking at it as it was 642 years ago. And so, because it takes light 642 years to get to us. So if Betelgeuse blows up, which many scientists think it will, if it blows up tomorrow, like you go outside and Betelgeuse is not there, well, you'll know because it'll be brighter than the moon. So we'll see it even in the daytime for a couple of weeks. Then it actually blew up 642 years ago. But if it blew up today and we didn't see it, that means we wouldn't know about the explosion until 642 years. So try to wrap your head around that time frame. Now, it's not the biggest star in our solar system. There are much bigger ones. There's Antares. Antares is much bigger than Betelgeuse. But it's much bigger than our sun. So look at where our sun is. Bring the page marker back. Let's use orange. Why not? So here's our sun. You can't even barely see it. It's a little dot right there, right? But look at these other stars, right? And Betelgeuse, a big red giant. But Antares, look at Antares. But again, there are even bigger ones. So here are the two biggest ones we've seen so far. For many years, it was just VY Canis Majoris. That was the biggest star in the sky until just recently they discovered another one. And again, they might discover more later on. You never know. But if these stars ever went supernova, ever blew up, and they were close by us, which they're not, thankfully, but if they did blow up, they would destroy our entire solar system, right? So this star is enormous. You wouldn't even see our sun. Yeah, I mean, I can't. If I made a little dot, that is actually too big. The sun would be even smaller than that dot. To tell you how gigantic these stars are. And normally, when you see stars that are this big, they don't have a long life. Usually, our sun, a middle-aged star, it's in middle age too, because it's 5 billion years old, and it probably has another 5 billion years left. Now, when thinking about the universe, we're thinking about, could there be life out there? And we talked about this in class. And SETI is a private institute. It's being funded to look for extraterrestrial life. That's what it stands for. Search for extraterrestrial intelligence. And they're searching. They're out there listening to see if they can find any kind of transmission. And there it is. Anything coming from space. And we also talked about the Dyson Sphere. And the Dyson Sphere is something that we can't create. We don't have the technology to create it. But if we had that technology, we can control our sun. And again, we're going to talk about this when we talk about space in a few months. We'll talk more about it. All right. So the speed of light, let me just write that down again. I said it before. It's 186,000 miles per second. It's always that speed. Nothing can go the speed of light. Remember, it's miles per second, not hour. And a light year is what travels in a year, which is about, that's the about sign, right? About 1,000,000,000,000 miles, 1,000,000,000,000 miles. And the speed of sound is much slower. Much slower. The speed of sound is 767 miles per hour. So you can see light is much more faster than sound. And Mach 1 just means the speed of sound. Okay. And our nearest star obviously is the sun, but the next closest, and the reason why I put R, because there's actually three of them, and most stars in our galaxy, and again the Milky Way galaxy, most stars have a twin, have a partner, except for our sun. It's all alone. But here in Alpha Centauri, there's actually three of them: Alpha Centauri, Beta Centauri, or Alpha Centauri B, and Proxima Centauri. And actually, if you want to be technical, Proxima Centauri is actually the closest. But when I say, if you put down Alpha Centauri on a quiz, we just mean those three stars. And they're about 4.2 light years away, so it takes light around a little over 4 years to get there. So when we see Alpha Centauri on a telescope, we're seeing how it was 4 years ago. And these stars, they are smaller than our sun. They're not yellow stars; they're red dwarfs. So they don't have as much heat energy as our sun, but they will live longer than our sun, right? It's 25 trillion miles away. So for us, for our technology, even though light takes 4 years, if we ever get a transmission that's not natural, and we know that there's life on Alpha Centauri, which we never found any transmissions, but if we did, and we got a transmission from them, if we wanted to go see them, right now with our technology, it would take 70,000 years or more. So look at this. This is the closest are the closest stars. I remember these stars have planets around them because all stars have not. Well, we don't know if all stars do, but we're finding planets around stars. So these stars could have planets, and they could have life. We're not sure about that. But if we wanted to go there, it would take 70,000 years or more. And here's our sun. Even though it looks reddish orange, it is a yellow star, 93 million miles away. It takes light 8 minutes to reach us. So when you're looking at the sun, which you should not be looking at the sun, but you can see the sun. That light that left the sun left 8 minutes ago, or a little more than 8 minutes ago, but roughly 8 minutes ago. And here's a comparison of the planets, and they're not this close. This is just a model to let you know. So we have the closest is Mercury, and it is the smallest. It's not the hottest, though. Venus is hotter because of the cloud layers. But again, we're going to talk about all this when we get to space. But I wanted you to know because if we look at Earth and we look at Mars, we know Earth is the largest of the terrestrial planets, not the gas planets like you see here. And you would weigh more on Earth than you would on Mars. You would weigh more on Venus than you would on Mars, too. That was one of the questions that I actually had to throw out. But here you see it. Here's a terrestrial planet. So we have Earth. Let's get our page thing up again. Right, so Earth is the largest of the terrestrials, not of the gas giants. And why don't we use I'll use that neon, why not? Or whatever it's called. So Earth, Venus, Mars. Now here's Ganymede, the largest moon. Ganymede. Ganymede is larger than Mercury. Here's Mercury. Titan is larger than Mercury. Right, and here's our moon right over here. Right, it's not the largest moon, but it is big. We're getting a call from Ganymede right now too. All right. All right. So now in part C, we'll talk about matter. We'll talk about the elements and we'll talk about matter. So if anyone is heading out to Io and these other planets and these moons, which we will talk about when we talk about space. Great job.